In this video, we're going to continue our discussion of register allocation, and this time we're going to talk about what happens when we can't successfully color the graph, in which case we have to do something known as spilling. The graph coloring heuristic that we discussed in the previous video doesn't always succeed in coloring an arbitrary graph, and it may well get stuck and not be able to find a coloring. And so in that case, the only conclusion we can reach is that we can't hold all the values that we'd like to in registers. We have more temporary values than we have registers to hold them. And those temporary values have to live somewhere, and so where should they live? Well, they're going to have to live in memory. That's the only other kind of storage that we have. And so we're going to pick some values and spill them into memory. The idea is that we have the picture in your mind should be of a bucket, and it can hold a fixed amount of stuff. Those are the registers. And when it gets too full, some of the stuff spills over and ends up someplace else. Now, when does a graph coloring heuristic get stuck? Well, the only situation in which it won't be able to make progress is if all the nodes have k or more neighbors. So let's take a look at our favorite register interference graph, the one we've been using in our examples. And now let's say that the machine we want to use only has 3 registers. And so instead of finding a 4 coloring of this graph, we need to find a 3 coloring. So let's think about how to find a 3 coloring of this graph. Well, if we apply the heuristic, we'll remove A from the graph, but then we're going to get stuck because once you take A out of the graph and its edges out, every node that's left has 3 or more neighbors, has at least 3 neighbors. And so there's no node that we can delete from the graph and be guaranteed to be able to find a coloring for it with the heuristic that we discussed in the previous video. So in this situation, what we're going to do is we're going to pick a node as a candidate for spilling. This is a node that or a temporary that we are probably, or we think we may have to assign to a memory location rather than to a register. And let's just assume, for the sake of this example, that we pick F. And we'll talk later about how to choose the node to spill. There's a number of different ways to choose the particular node to spill. But for the illustration of this example, it doesn't matter how we pick it. We just have to pick one to remove from the graph. Okay, so we're going to say we're going to remove, that we're going to spill F. So what we'll do then is we'll remove F from the graph just like before, and then we'll continue with our simplification. And this will now succeed because once we remove F from the graph, we can see that all the nodes, well actually several of the nodes have fewer than 3 neighbors, and so B and D both only have 2 neighbors. Once they're deleted, E and C will only have 1 neighbor each, and so clearly coloring will now succeed. And here's one order that will succeed with this reduced graph. After we decide to spill F and we successfully color the subgraph, now we have to try to assign a color to F. And it could be, we could get lucky and discover that even though F had more than 3 neighbors, or 3 or more neighbors, when we removed it from the graph, it could be that when we go construct the coloring for the subgraph, that those neighbors actually don't use all of the registers. It could wind up being that all those neighbors, for example, are assigned to the same register, and so there are plenty of registers left over to assign to F. And so this is called optimistic coloring. So we pick a candidate for spilling, we try to color the subgraph. Once we have a coloring for the subgraph, then we see if we just get lucky and are able to assign a register to F, in which case we can just go ahead and continue to color the rest of the graph as if nothing had happened. So in this case, let's take a look what happens. We're going to add F back into the graph and look at its neighbors, and we see that we have a neighbor that's using R1, we have a neighbor that's using R2, and we have a neighbor that's using R3. And so in this case, optimistic coloring will not work. So in fact, F had more than k neighbors, and after we color the subgraph, it turns out that those neighbors are using all k, in this case 3, all 3 of the register names. And so well, there is no register left over for F, and we're going to have to actually spill it and store it in memory. So if optimistic coloring fails, as it does in this example, then we spill F. So what we're going to do is allocate a memory location for F, and typically what that means is that we'll allocate a position in the current stack frame. Let's call this address FA for the address of F. And then we're going to modify the control flow graph. We're going to change the code that we're compiling. So before each operation that reads f, we're going to insert a load that loads from that address the current value of f into a temporary name. Okay, and that makes sense because if the value is out in memory, then if we have an operation that needs to actually use the value, we're going to have to load it from memory first into a register. And similarly, after each operation that writes f, we're going to insert a store. So we're going to save the current value of f into its location in memory. So here's the original code from which we constructed the registry interference graph. And notice that there's a few references to f in here, and we just highlight them. All right, so we have a couple of reads and we have a write. And so now, what are we going to do? So here we had the use of f, the read of f in this statement, and now we've preceded that by a load. And notice that I've given a new name here. I've called this f1. And that's because the different uses of f in the control flow graph don't all have to have the same temporary name. And actually it will be a good idea to separate them. So each distinct use of f will get its own name. So here we load the value of f, and then it gets used in this statement. Here we have a write to f, and so we store the current value of f. And notice here I've given it a different name, f2. So the temporary that's computed here that's going to be stored is called f2. And finally, there's the third use of f. There's another load of f right here, which is then used in this computation here of b. Okay, so that is a systematic way to modify the code to use f in storage. And now we have to recompute the liveness of f. And so what happens there? Well, here's the original liveness information from which we computed the register interference graph. Okay, and now notice that f is gone. We no longer use f in the program, so we can delete all the places where we mentioned that f was live. And now we have the three new names, f1, f2, and f3, and we have to add in their liveness information. So we've created some new program points here where we inserted statements, and of course where we have a load of the current value of f, that value is live right before the use in the next statement. Here we have the write of the current value of f, and that's live right before the store. And then here's another load of the current value of f, which is live until the store, until the use in the next statement. Okay, and so now notice here that f used to be live in many, many, many places in the code, and now not only is f or the different versions of f live in fewer places, also we've distinguished them. So we've actually separated the different uses of f, and so these will have their own nodes and their own set of interferences in the graph, and they won't share them with the other uses of f, and that will actually also reduce the number of edges in the graph. To summarize the example on the previous slide, once we have decided that we're actually going to spill a temporary f, that means we're going to change the program. We're going to add loads and stores to the program, and now we're going to have a different program, and that's going to change our register allocation problem. So we're going to have to recompute the liveness information, we're going to have to rebuild the register interference graph, and then we're going to have to try again to color that graph. Now, it turns out that this new liveness information is almost the same as it was before. So all the temporary names other than f are not much affected by the new statements that are added. There's just a few new program points where they might be live, but every place they were live before, they're still live. And f itself has changed fairly dramatically. Its liveness information has changed fairly dramatically. Certainly the old name f is no longer used, and so its liveness information goes away. And then we've also split f into in this case, three different temporaries, one for each of the different uses of f in the control flow graph. And now notice that each of these new uses of f, or these new versions of f, is live in a very, very small area. So a load, for a load instruction, the thing that we're loading, the temporary that we're loading, fi, is live only between the load and the next instruction where it's used. And similarly for a store, the store of a temporary fi is live only between the store itself and the preceding instruction, the one that created fi. And the effect of this is to greatly reduce the live range of the spilled variable. So whatever name we decided to spill, by adding the loads and stores right next to the places where those values are used, we dramatically reduce the live range. And in addition, as I mentioned on the previous slide, by splitting the name f into multiple different names, we also avoid sharing those different live ranges between the different versions of f. So because the live range of f is reduced by spilling, it has fewer interferences in the new program than it did in the old program. And what that means in particular is that in the rebuilt register interference graph, f will have fewer neighbors. Some of the neighbors that it had before have gone away because it's just live in fewer places. So if we look at the new register interference graph, we can see that among all the different versions of f, so remember that f has been split into 3 temporaries in this graph, we see that they only interfere now with D and C, whereas before f had several other neighbors in the graph. And now, in fact, this new graph is 3-colorable. Now, of course, it might be the case that we can't just spill one name. We might have to spill several different temporaries before a coloring is found. And the tricky part is deciding what to spill. So this is the hard decision that has to be made during register allocation. Now, any choice is correct. It's only a question of performance. So, some choices of spilling will lead to better code than others, but any choice of spilling is going to result in a correct program. And there are some heuristics that people use to pick which temporaries to spill. And here are a few, or I think 3 of the most popular ones. One is to spill the temporaries that have the most conflicts. And the reason for that is that this is the temporary, the one thing that you can move into memory that will most affect the number of interferences in the graph. So the idea is by possibly spilling just this one variable, we'll remove enough edges from the graph that it becomes colorable with the number of registers we have. Another possibility is to spill temporaries that have few definitions and uses. And here, the idea is that by spilling those, since they're not used very much, the number of loads and stores we'll have to add will be relatively small. And so if a variable just isn't used in very many places, then the actual cost in terms of additional instructions that are going to be executed to spill it is relatively small. And another one, and this is actually one that I think that all the compilers implement, is to avoid spilling in inner loops. So if you have a choice between spilling a variable that's used within the innermost loop of the program and one that's used someplace else, you'd probably prefer to spill the one that's used not in the innermost loop, because again, that will result in fewer loads and stores. You really want to avoid adding additional instructions to your inner loop.